Daisy and ISP for the ILC. It's my pleasure to introduce to the speaker, Professor Koushik, and he'll be speaking on traffic clearing games in Internet exchange points. Dr. Koushik is a professor in the Electrical Computer and Systems Engineering Department at Rensselaer Polytechnic Institute, Troy, New York, where he has been a faculty member since 2002. His primary research interest is in developing and analyzing network algorithms that can be implemented in a decentralized manner through local coordination, only requiring limited information about the network topology and conditions. His recent work is mostly on the study of resource pricing and economic efficiency questions related to use of shared resources like bandwidth and energy by self-interested agents with applications to the internet and smart grid. Professor Paul received his BA degree in electrical engineering from IIT Kanpur and his MS and PhD degrees in electrical and computer engineering from the University of Maryland, College Park, respectively. Professor Paul received the Career Award from the National Science Foundation in 2005. He has won multiple base paper awards in international journals and conferences and has been on the editorial board of several top journals in the field of communication and networking. We request the online audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box to read your questions. Over to you, Professor Paul.
Thank you very much for the introduction. I hope you can hear me, those in this room and those in the audience. Those audience, I'm not able to see you right now the way it's set things up, but if you have any questions anytime, feel free to unmute and ask. So it's a pleasure being here today. Last time I visited IISC probably 8-9 years back. So today I'm going to talk about traffic clearing games and internet exchange points. So this is joint work with a couple of my faculty colleagues, Elliot Angelevich from RPI, who's a game theorist, computational game theorist from computer science, Murad Yüksel and UCF, who is more of a network systems person, and my PhD student, Mohammad Ibrahim Alam, who just graduated, and he's just started as a postdoc under me, as also visiting Yale at this time. So the slides are mostly done by Ibrahim, although I made some changes. So this is slide I had. Okay, so this is an overview of what I have done over the years. I've been in research since I started the PhD. I graduated from IIT Kanpur and started PhD in 1997, so it was a long time. So I started working on video streaming, caching, and inter-domain traffic engineering. I was an instrumental at that time. I was collaborating with Bell Labs and so on. And then over the years, my interests have changed a bit. Like with what topics have becoming more and more timely, more interesting, and so on. And here is a brief overview of what I have done. So I've worked primarily through my career on 4 different broad topics. One is internet traffic flow optimization and pricing, which is I'm going to talk about today, and wireless and sensor networks, and a couple of problems on those sides, mostly until about 2014, 2015. But there's a couple of topics still in that space, particularly wireless spectrum trading and pricing, which I'm starting to explore again. So if you see the arrows which is lightly shaded, those are the topics I'm starting to explore again. But you won't see any recent papers, but probably be coming up soon. And then in collaboration with power systems engineers and mechanical engineers, scheduling a flow optimization in power and thermal grids. Okay, so these are also scheduling and control type questions. And also more recently on machine learning for networks and networks for machine learning. Again, one topic I've been exploring with IBM, and another I'm just starting to explore. So that kind of gives you what I've done over the years. There's one topic I have continued to explore over the years, and that means pricing, traffic pricing, and traffic optimization. Okay? Although the flavor of the problems have changed from intra-domain traffic engineering to more intra-domain traffic engineering between contracting between ISPs, internet service providers, and pricing issues and so on. So that's what I'm going to talk about. I mean, all these topics look very different, but there is some common themes that tie all of these. These are all control and optimization network systems. Most of these are packet networks. Some of these are energy flow networks as well. And the common tools that are utilized are nonlinear stochastic optimization and more recently game theory, mechanism design, and so on. So a bit of a background of why these problems, why the space is interesting. I mean, all the work that is presented here is my PhD student's work. That's pretty much his complete thesis. Okay. So, but why? What is the space? So the background is, we get internet service from internet service providers. We all know that, right? So we are connected to some internet service provider, which is usually a customer service provider. And then they connect with other service providers to other service providers and so on. And these days we are usually getting content from content providers. It could be Google, it could be Netflix, it could be Apple, and or cable TV companies, whatever, right? So all these are now streaming data to us and this we see here, CP1, CP2. These are content providers, and then we are connected to access networks. In between, there are transit service providers, and these are big providers. Some of these could also double as access providers, like AT&T and so on in the US. I know the US system better, so I'll give examples from that. But access providers could be different as well. And now, a lot of these transit providers have really large backbones, often telephone companies that we are now becoming internet service companies, like AT&T, right? Now, this was an old system. Now, in between, since the 1990s, early 2000s, came in this picture, content distribution networks. Okay, there were services, companies like Akamai would put servers all over the world and get content from the content providers and store locally. It's like caching in a way, right, at the internet scale. That became very popular. Why? Because people wanted content fast. So getting it from the content provider, traversing a lot of these ISPs was time consuming, right? So content distribution networks wanted reduce the time of access. But slowly, what has been happening for the last 10 years or so, the content providers becoming really, really big, and they don't want to deal with this CDN layer anymore. They want direct access to the customers. Now, they cannot have direct access to the customer. They have to go to the access ISPs. So they are forming peering relationships with the access ISPs. So the yellow, yeah. So the red dotted line that you see, that is a peering contract. It does seem vertical, but it's really a lateral contract. Peering means no exchange of money. Okay. So I benefit you, you benefit me, and therefore it's there. Now, peering contract need not be between customer provider and access, so content provider and access. It could be between access providers, access networks as well. That is that you see the horizontal lines. Okay. Now, why is that better? Okay, for two reasons. First of all, it gives direct access to the content, which is faster instead of going to the transit. Not only that, financially it's also better because access, whether you receive data or you send data through a transit provider is providing a service, you pay money. Okay? It doesn't have to be on a byte or packet basis, but overall, more traffic you send or receive, you pay money. So peering contracts are great, right? So it saves you latency, it saves you money. Okay, so that is kind of what is going on lately, and that is the model we'll analyze. Okay, so there will be transit services which you kind of pay for, and there are direct peering services. But there's no free lunching, right? So when you do these peering services, you have to go to a point called IXP, Internet Exchange Point, to peer, and the ISP charges someone. Okay, so your other ISP doesn't charge you money, but the IXP, the Internet Exchange Point, which is a meeting place, that charges someone. Okay. But still, increasingly, what is happening is increasing that peering is happening through Internet Exchange Points to the extent at this, I mean, estimate this is still a few years back, 70–80% of the traffic in US and a sizable proportion of the rest of the world actually goes through Internet Exchange. Transit, and that is despite the transit costs are falling. The transit costs are reducing, but still people like to peer. Okay, and partly because of the lower delays. Okay? However, recently another trend is happening is some of these peering contracts are translating to what is called paid peering. That's why you see here an arrow. Okay, so content providers and access providers, they are saying, well, and actually access providers are telling content providers, like say Google, saying you guys are making a tons of money, and I'm running all the network to support your traffic. I'm getting paid nothing. So you pay me, and that's has been on the rise. Paid is still peering, but one pays out. It's not really true peering. Like there was a big famous case, maybe 5–6 years back in Netflix and Comcast. Netflix, the content provider, Comcast provider, Netflix was forced to pay money to the Comcast to reach the Comcast customer. Okay. So that is some of our work, although I won't talk about it today, does cover paid peering. Now, what is projected in the future might be what my colleague calls is, my collaborator calls it sugarcane ISPs, where the architecture like this, content providers are peering with content providers. That is possible when you are drawing a lot of your content from a single content provider. Like you might be in the Google ecosystem, or I might be in the Apple ecosystem. And that is kind of in a way happening, right? We have all these, I have all these Apple devices and everything together. And of course, I get content from elsewhere as well. But suppose I also subscribe to Apple Music, Apple TV, and all these, right? So then I just need a fast connection to Apple servers. Now there might be some extra content I still need that will also come from Apple, but maybe from Google or Netflix, and that will force the content providers to peer each other. So it's possible that it will evolve that way. Okay? But our model mostly targets this and a little bit of this, which is a current trend.
Where is the IXP in the figure?
In this figure, IXPs are not there. Okay, yeah, they are coming. Okay. So this picture is, the left-hand picture is where all the internet exchange points are located. Okay, which is the meeting place of the ISPs. The ISPs go and meet with each other and exchange traffic. These are usually just plain peering. Some of these could be paid peering as well. You can't get all this data, but you know which ISPs are present at which IXPs. There are about 134 IXPs in the US. Okay? A lot of these are operated by a for-profit company called Equinix, which we talked to, although they didn't collaborate with us. They gave us some valid inputs. In the European market, however, it's mostly non-profit IXPs, which are just trying to do cost recovery. Okay? So, some earlier papers, dating back, 2015, 16, we analyzed non-profit IXPs. But with this current student of, recently graduate student of mine, I just explored for-profit IXPs, where the problems are also more challenging, more interesting, like Equinix. Okay? Now, the sizes depend how many ISPs are present at the IXP. Some of these are big because lots of people meet there. You will see a lot of presence in around the DC area and in California and so on, not surprisingly, and so on. So this is a schematic. Two ISPs shown by this cloud might connect at different points, different IXPs, and then have to also decide, how much flow, how much of traffic to send through this IXP versus that other IXP. Also, where to choose, because they might be, they might have, they might participate in 5 different IXPs, but they do not need to peer in all 5 IXPs. They might say, okay, we just participate in exchange peer in 2 of these IXPs, although they are present, in 5 different IXPs. That's possible. So that's also a decision problem we'll handle. So, it takes it, IXPs are really big data centers. Like big data centers. This is one of the IXPs run by Equinix in Sunnyvale, California. The huge data centers. I wish I had a picture, but they prohibit you from taking pictures. But it's multi-story building with what they call cages. Okay. So cages is is just a room with which is netted, okay, and locked. And you have the server. You don't want to close it because that will generate too much of heat, right? So it's an open frequency for the servers, and you can rent a cage and you pay the price for that. But the bigger price you have to pay is for the connections from the server in that cage to a switch fabric. Okay, so IXP runs a huge switch fabric, and in that building where all the servers in each of these cages go, and you pay mostly, of course, for rental of the space, but more importantly, for the bandwidth of the pipe that connects your server, your cage to the switch. Okay, if you want faster connectivity, you pay more, right? And there are some established prices. So we are going to question that, how this should truly be defined, how this pricing should be defined, what their market efficiency and so on. So that's the question we will talk about. It's divided into 3 parts. First is the pricing policy of the IXPs. How should IXPs be charged? Right now, it's not born out of any mathematical analysis. They decide, okay, this is the good price to have, and so on. We'll analyze constant pricing, proportional pricing. We'll also talk about specifically before purchase the IXP. Okay, so in the first one, which we started, which is a simplified version of the actual problem we wanted to solve, because we're solving it, just trying to get a grasp of the problem. We say that the amount, the price you pay depends on the traffic. Okay, you are going to send. Okay, the implicit assumption is finally you really have to purchase by the bandwidth of the pipe or the port capacity, the connection of the pipe carrying your traffic from your cage to the switch port. Okay, but we are not directly addressing the port capacity problem. We are kind of implicitly saying that you decide how much traffic will send, and then provision the port capacity based on that. Maybe 30% more or whatever. Usually you don't load your pipes more than 70%. Otherwise, it will be terrible deals. Okay. And the results are nicer in a way, but the model is also restrictive, and the model is generally certain, the model is also restrictive in some other way. We'll see that. Okay. And there, the port capacity and the traffic are treated as independent variables, not directly depending on each other. Okay. So those 2 works I will describe. I'll probably describe the first one. It's a little easier to describe in more detail. Second one, I will kind of summarize just the main results to give you a feel of things. And then another piece of work where we talked about we formulated the problem of where you should peer, or whether you should peer and where you should peer. So the first 2 is assumes that you have already decided to peer. The question is, or you're already present in an IXP, and you're deciding whether should I send the traffic to the IXP or I will send traffic through the transmission. In addition to IXPs deciding what the prices they should charge, and they are interrelated. Okay. In the third one, we are trying to decide 2 ISPs, should they even if they're present in some IXP, should they peer at all or not? And if they decide to peer, where among these multiple IXP points they should be? And that is driven by more data analytics, more machine learning. Okay. So first, the pricing policy of IXPs. The IXPs internet exchange points charge a fee for ISPs for cost recovery or for profit. In this case, we'll deal with a profit-making ISP like Equinix. Now, how they charge particular profit-making ISPs make a big difference to the efficiency of traffic, which is not appreciated so much. The work was actually triggered by one more experimental systems-oriented paper in SIGCOMM around 2014, 2015. There are a couple of systems papers before that as well, and a few papers after that as well. But mostly from the systems guys, we realized the importance of this theory. Okay? But we are probably the only group who have analyzed in the mathematical way. But of course, we are trying to put a model to that and analyze it, but that means we have to make some simplifications from the actual practice, and we'll talk about some of them. Okay, so we're going to talk about stable and efficient peering, okay, at these internet exchange points. Now, as I said, so in practice, ISPs pay by the port capacity they purchase. Okay, but usually, you would think, right, if you are sending 10 megabits, 10 Mbps. Or maybe 10 is too small, let's say 10 gigabits per second, right? You won't go and rent 100 gigabits per second, right? You'll probably, try to get, 20 megabits per second, 30 megabits per second, right? So those should be related, yeah? Anyway, so, and then, so we'll deal with that. First, we'll talk about pricing, just the pricing, and then, and then we'll talk about the peering. Okay. So the first two pieces of first two parts of this presentation, the topics 1 and 2, is heavily on the game theory. So how many of you are exposed to some game theory? A little bit, okay, yeah. So it's not it's not always that game theory courses are offered in engineering, although we have a bone theory course being offered. Right? So let me explain a little bit, okay, but I assume all of you know some sort of optimization, right? Or using optimization using MATLAB and stuff like that. Game theory is a little bit different. Here we are not trying to find the optimum point of an objective function, but you have different agents who have different objective functions, and they may not be the same. So my objective, I have a selfish objective. I'm a player, you are a player, you have another selfish objective. And our objectives are not the same. So but they are connected. I will try to make a decision to minimize my own objective. You will try to make a decision to minimize your own objective. The question is, as we do that, so I'm taking an action seeing yours, you're taking an action seeing mine. Now, does the sequence of action, does it reach an equilibrium or not? It may not always reach an equilibrium. Okay. Now, if it doesn't reach an equilibrium, that's no good. Okay. But fortunately, in all these traffic pricing flow grain, they have an equilibrium. Sometimes they have multiple equilibrium. Then, if there's an equilibrium, the question is then, how good is that equilibrium from the objective of minimizing the overall cost of the system or maximizing the overall efficiency of the system? So if there was a centralized entity who would optimally solve this problem, okay, then you could come up with a solution. But this distributed agents, solving the problem in self-interest, they reach an equilibrium. Okay, how good is the equilibrium compared to the system optimum? Okay, and that is often captured by what is called price of anarchy. So anarchy, because everybody is doing things on their own self-interest, right? That's why the anarchy exists in this game theoretic setting. And what is the price for that, as opposed to a centralized government, solving the centralized government? In this case, is unrealistic, because that means there will be one entity solving the problem across all ISPs of the entire world, okay, which are all private businesses, and they won't agree to that, right? So here the players are the ISPs. Okay, there's also the additional player, which is the IXP operator, like Equinix, okay, which is making the market, but also charging a price. So there are, agents, the players, all ISPs at an IXP and the IXP itself, okay, which is also profitable. Okay. So we often characterize this with the price of anarchy. Okay. Now we'll try to compute the POA. This is a standard in computational game theory. This is a very standard measure. POA is a worst case performance at equilibrium. Now, in this case, because you are, as an internet user, you are interested, or if somebody is overseeing the internet, you're interested in the overall social welfare of all ISPs, or which means also all the users. So you want to have a small POA. Okay, if small POA means POA close to 1 is great, right? Ideally, it should be 1, but it's not the case. But on the other hand, if you have a solution which is terrible in terms of revenue to the IXP is going to back. Okay, so you also want a good POA close to 1 ideally with respect to revenue. Okay, and often they contradict each other. Or another term we often use is social cost. Now, social cost and social welfare are related. One you minimize, another you maximize. They are related to each other. You can choose either one. It turns out it depends on the problem. Sometimes dealing with social welfare is easier, sometimes social cost is easier. In fact, you will see as we go through the different topics, topic one, in topic 1, we deal with social welfare because it was that was the only metric that was giving us some reasonable results. Later on, we just moved to social cost for the other models. So basically, you want to have a good trade-off point between social welfare or social cost and revenue, which are kind of contradictory. So social welfare, social cost is the aggregate utility across all ISPs and therefore for all users. And revenue is the utility of the market maker, which is the IXP. Okay, to keep all of them happy. Okay. So there have been some related work on the space, selfish routing and congestion games. I won't go into all the details. There are certain technical differences. Some of these are actually quite big differences between our model and what has been done. Our model is closely related to what's called network formation games, but those are discrete games, whereas ours is continuous games, and that makes a big difference, and so on. So, and people have not considered the IP set. Okay. So, with that background, let me go over overview of the three pieces. Again, this part will be difficult. Some of this is very technical in game theory. You have not worked in game theory, and specifically on this, it will be difficult to appreciate. But I will try to give a high-level intuition about what is going on and what are the main results. Okay. So these have been published in a bunch of papers, conference, and a journal paper, and in transactional networking. So first we analyze a constant pricing policy. Suppose the ISP is charging a constant price per unit traffic, and agents are responding in self-interest. So how good is that? Okay. So setup is like this. You have an IXP. It's charging a price P as a function of Y. Y is the total traffic going through the IXP. And ISPs also encounter a delay dy. Okay, it's a function. Y is the total traffic across all ISPs that are exchanged to the IXP. So aggregate cost is CY, which is PY plus DY. That's the aggregate cost the ISPs are facing. Now note that when Y goes up, this cost goes up. right? And which makes sense, right? Because if you more and more people send to the IXP, it's a shared switch. The delay will go up, okay? And the IXP should also be charging more money, right? Because there's more congestion, it has to control congestion, right? So PY goes up, DY goes up. So therefore, CY, the total cost goes up. And at that point, it may not be beneficial to send any more traffic to the IXP. So at that point, maybe you should be sending traffic to the transit path. Now, why is the transit path bad? Okay, transit path because you pay money for that. Okay, but I say transit cost will decline. But more importantly, the paths are longer because going through several tiers of ISPs and so on, and it'll be a delay. Okay, so think of this lambda ij as a transit cost, mainly in terms of delay, right? So so the question is now the trade-off, right? So each ISP is deciding, each ISP pair, I and J, is deciding whether it should send its traffic through the IXP, provides not too congested, or send it to the transit path. Now, this is being done by all ISP pairs. The traffic is decided by my ISP pair. I cannot be sending you traffic if you don't agree to receive on the ISP, okay? Or you cannot be sending me traffic, right? So it's mutually decided. Okay? So that's why these are analyzed as pairwise equilibrium. Okay? Which is not very usual for the networking context. In the algorithm, some people have considered pairwise equilibrium for network condition. So we're the first to use this in this context. So which is different from Nash equilibrium, whatever Nash equilibrium. The standard Nash equilibrium. Okay. So anyway, so that's kind of a game. Okay. So I would skip all these terminologies and so on. This is from my student's thesis. So he wanted.
The cost is in your problem.
Yeah.
Traffic plus D.
Which one?
Cost.
Cost to the IX. So this is yes. So this is social welfare. So if you revert it, okay, so then it gives a cost. I will have our expression later.
So welfare in this case would be the linear combination of.
Oh, the W.
Yeah, I will say like SW is the welfare.
Oh, welfare. Yes. So welfare is is the utility gained by sending flow through the IXP. If you send YIA through the IXP, then you're saving on the transit delay. That's why you put here as a positive here. But that delay, the traffic going through the IXP, you pay a price PY for that, and they do have a delay DY for that. So that's a negative. So that's a cost. And the gain you are having by not sending to the transit, that you put in the positive side. So that's the total social welfare, which we want to maximize. That's a social optimum. But due to this greedy, selfish nature, that's not going to happen. Okay. So here is kind of I won't explain this, right? But this is basically some kind of inverse demand curve. Okay. So they're different ISPs have different transit paths, and they can measure the delays, end-to-end delays, and get an idea of how much delay they can be saving by sending to the IXP. Okay, how much of transit delay. Okay, and those are the lambda ij values, and lambda ij values you can order them. Okay, so now if suppose you charge beta e, IXP charge beta e price per unit traffic. Okay, so the beta e, so the true cost is beta e plus dy, right? Dy is the delay, right? Beta we are dealing with constant pricing. Okay. So this curve looks like this, right? So at that point where this cuts the lambda curve, anything above that, those are very high delay traffic in the transit path. They will still go. They will still go through the IXP. But anything below that, all the ISP pairs would transit, the delays are not that large, right? They will try to use a IXP, right? So you hit an equilibrium point like this. Okay. But what you're interested in is a social optimum point, which is this. okay, which comes from this, the social welfare we express. So this you take the derivative, and you get this e prime y, and you want this, if you want to be this one, and that's contradiction, right? So you want, but you could say, well, why don't we just define beta e as beta p? Beta p can be calculated given this lambda curve. The problem with that is the following. Okay, if you try to do that, the revenue earned by the IXP will be terrible. So suppose I estimate the lambda curve, and there are ways of doing that. I calculate beta p and go to the ISP, IXP, internet exchange point, go to Equinix. Okay, so and let's say, why don't you use this beta equals beta p? Beta p I can explicitly calculate. It won't do that because it will lead to terrible revenue. So what do we do? Okay, so we want beta e to be close to beta p. Okay, for social optimally, but we also want a point that which is revenue would be good. Okay, and that's a very fundamental trade-off. You cannot have it both ways. So you have to have a compromise. Okay, so it turns out the nature of these curves make a big difference in terms of how good a trade-off you can get. Okay, and these lambda curves, I'll show some realistic lambda curves later. Okay, if they become too convex, that's a problem. Gives you terrible results. Okay, but fortunately, they are not too convex. They are often, we'll see, they are kind of convex concave. But what we could show is, we can, if we parameterize the lambda curves, how convex, how kind of bent downward, how much below the linear curve. Linear curve is this. If you join, these are normalized. You join 1, 1, 1, 1, 0 with 0, 1, get a linear curve. How much lower they go compared to the curve. If you parameterize that, the results, the PO values come in terms of the parameter. Now, there are two ways of characterizing that. You think of this line is joining 1, 0 and 0, 1. Push it down until the lambda curve goes above that. Okay, that is called the shift factor. Okay, or you try think of a rubber band tying from 1, 0 to 0, 1, and you're pulling that rubber band and see how much you can pull. You have to pull so that the lambda curve goes above that. Okay, and lambda curve, as I say, is just a ordering of all the transit delays and how much of traffic faces that transit delay. So let me go back to the lambda curve again here, or I can explain here. So this is a lambda curve. Essentially, at the top, this amount of traffic, or maybe a discrete version, we are approximating this continuous one, but so this amount of traffic here has a very high transit delay. The next block of traffic has this amount of traffic, transit delay. The next amount of traffic here, okay, has this amount of traffic, has this amount of traffic. Okay, so you order them and see how much of traffic has that delay, and you form this lambda curve. So with all these results are with this lambda curve. So and then you get some results like the results look messy, but bottom line is, if you choose the parameters carefully, it can be at best like 3 over alpha 1, and then if it's alpha 2, if you use the other stretch factor, then if you use the shift factor, it's 3 over alpha 1. If you use the stretch factor, then it's this formula, which is now in the ideal case, if alpha 1 and alpha 2 1, this is like 3. So POS 3 is not terrible. I mean, ideally you want to get very close to 1, but note that this is worst case. In practice, this shows some lambda curves for different IXPs. Now, some of these are based on data from CADA and peering DB, which does measurement and posts them for public use. But there's some part which requires traffic demand estimation. That way to use some models from existing papers. So that's not exact. Okay, but the locations, the ISPs, the IXPs, and that presents where they're located, and They are router distributions which we are taking as proportional to the demand. If there are more routers in a city, we expect that they probably handle more traffic. That's all. So there's some approximation being done and with some existing published models. We get these lambda curves. Okay? So these lambda curves means there is a little bit of traffic which is a very high transit going on really long paths. After that, it's kind of smooth, and towards the end, there is a lot of traffic. There's a little bit of traffic that has this sort of delay. But this is very typical. It's kind of a convex and then becomes a concave. But and then the alpha 1, alpha 2 is, if you take a rubber band again, stretch it down, it has to contain the lambda curve, all the lambda curves, or the specific lambda curve above it. So if you do that, alpha 1, alpha 2 is going to come to pretty pretty low values, not great values. So the worst case bounds won't be that great. However, what we observe is in practice, in numerical results, the actual results are very good. Okay, if you look at the POA values here, and this is for we use two different delay functions, polynomial delay function and queuing delay functions. They are within like 2 to 3. Okay, and if you choose the value of k, and so beta a has the parameter by some constant k. So if you choose a value of a certain parameter, you can make it like 1.5. Okay. Now this is for social welfare, and the same for revenue. Okay. So now you can go and tell the IXP that if you use this pricing policy, you would be no worse than 50% of what you would get optimally, right? And at the same time, it's across all ISPs, their utility is also no worse than 50%. Okay, so like 1.5 factor, right? 50% more worse compared to the optimum for both, which is not a bad trade-off. Okay. Okay, so that's constant pricing. But that all sounds good, except that it requires a knowledge of the lambda curves, and it's very difficult to get it exactly. Okay. We generate all the lambda curves for ISPs, but it's based on certain assumptions. It may not be the true lambda curves. So we wanted to come up with a policy where the pricing doesn't have to have the knowledge of the lambda curve. And then we came up with one which works surprisingly well. And now again, I will skip all the math and so on, but it's proportional pricing. It simply says whatever the delay in the switch is, just charge it in proportion. Okay, so you have a DY. So earlier I talked about ISPs paying PY and DY, coordinate traffic. We are saying make PY proportional to PY. Okay, and by a factor beta minus 1. So essentially the total cost becomes beta times, right? So beta has to be greater equal to 1. So that we analyzed, and we got some bounds for for polynomial delay and queuing delay. But what we observed is summarized in this picture. So so for a proper choice of beta, which is like 3 to 4, the peer for the social cost. Okay, so again, social cost here is social cost is very much like it's the inverted social welfare, but except that Bij is the total demand for going from ISPI to ISPJ. So that is added up. Okay, this is more of a technical thing. But think of just it's the inverse of social welfare. Okay. Social welfare, we're maximizing social welfare cost, we are minimizing. It's more for the analysts to work out. Anyway, so social cost we want to minimize, okay, and the POA values we want to be close to 1. If you look at if beta is around 3 to 4, they are pretty close to 1.2. And at the same time, the revenue is also not too bad. It's still 1.1 or 1.2. Now, revenue we could not theoretically bound in for proportional pricing, but simulations show that these are pretty good. Okay. So what is the conclusion? The conclusion is for the right beta, and which is like 3 to 4, which means beta minus 1 is what you're charging. So like 2 to 3. So charge ISPs roughly 2 to 3 times the cost of the delay. Of course, these are not, the one is delay, another is price. So there will be some proportionally constant, some scaling constant there. But roughly, if you do that, then you don't need knowledge of the lambda curves, and that gives you even better view. Okay, so for both, roughly only 20% excess, more than the optimum for both. Whereas the earlier ones we were getting on 50%. So that's kind of a nice result, but that skipped. That assumes that the port capacities and the traffic rates are related. Okay. Suppose we treat them independently, then what happens? So then it becomes this part I'm going to quickly go over. I mean, technically this is much more challenging, but essentially it's in the same vein of work. So here the problem is a little bit complicated because we're not only choosing the traffic rates, but we are also choosing how much the bit pipes, the widths of the bit pipes, and the port capacity you're purchasing. Okay? And now you have to consider port congestion. Okay, how much delay they account. So earlier we were considering delay in the switch. Now you consider delay at the ports as well. Okay? And the ports are, there's one port for incoming traffic, there's one port for outgoing traffic. So 2 different ports. Okay. So a traffic pays delay at the port going into from I to J. At this port I, then delay at the switch, and then at port J. The traffic coming from J again at port J, then at the switch, then at port I. And as for IJ traffic, I care for both delays, this direction and that direction. That leads to all these jobs. Plus, there is a cost for purchasing the port. Okay, that's leasing the port. And there's a transit cost for whatever traffic I cannot send. Bij minus Yj, it goes to the transit that into Bj. So this determined proportionally, like we did earlier. So in this work, we are not analyzing the revenue part. So it's just the social welfare. Earlier, we are considering revenue as well. So pricing policy was a big deal. So here, we are assuming the pricing is given. And surprising the results we have for social welfare, not revenue. For social welfare, it doesn't matter what this pricing is. It's for a very broad range of pricing, the social welfare is good. But of course, if we consider revenue, then that will be critical. That's a part that still remains to be done. So let me quickly go to the go over the results. I'll just focus on the parts that are highlighted in there. So this is a difficult problem. So we started step by step. We first assume that the transit option is not even available. Of course, it's available always, but just for the sake of getting a handle of the problem. For that, we could show it's what is known as a potential gain. It's a very standard form of gain, and there's a unique equilibrium, and the POA in that case is also called the price of stability. Price of stability is the best equilibrium that you get. Is bounded by a factor of 2, which is also considered good. Now, and that is when the switch capacity is fixed. Then we started assuming the switch capacity is variable. Switch capacity means if you purchase more port capacity, the ISPs purchase more port capacity, the IXP is forced to upgrade the switch as well, which is normally what will happen. You won't sell more port capacity while keeping a switch fixed, because that will really create conditional switch. Now that became very hard to handle. But under the different techniques. Okay? But finally, again, we are attacking the problem one step at a time. Finally, we said we are going to deal with the problem with the full flexibility, where the port capacities are purchased and the traffic are decided separately. But of course, you have to make the port capacity more than the total traffic you send. Now that becomes a unilateral bilateral port hybrid game, which is not, at least I don't know of anybody who has handled that sort of game. However, in this case it simplifies a bit, because the port capacity becomes a function of the traffic rate you send, okay? Helping us utilize some of the results we have, some of the analysis methods we have used earlier, right? So on topic 1, and we were able to get a bound of without any considering the switch. Suppose the switch delay is not the bottleneck at all. Then, depending assumption, we could get a bound of 2 or 4. In the worst case, we got a bound of 8. Okay? I mean, that seems very bad. But let's see what happens. These are all worst case results. But let's see what happens in our simulation results. In the simulation results, it wasn't that bad actually. It was. Yeah, actually, yeah, in the simulation we got as bad as 1.8. So, yeah, the results are not as good as before, but that was a different game. There we got 1.2. Here it's going to close to 1.8, but still it's much better than the bound of the worst bound we got is, for fully general cases 8, right? So it's 1.8 versus 8. So it's still much lower than the worst case of it. Okay. So, yeah, so these are the bounds. Again, these are worst case bound. In practice, it's better. So I have about 7 minutes left or so. So let me talk about topic 3, okay, and then conclude. Okay. So again, let's recap what we talked about. First, we talked about the pricing policy at the IX, and based on the pricing, the ISPs decided whether to send their traffic to the IXP or through the transit. Okay, and we argued that if the IXP is charged proportion to the traffic, okay, that's a very good policy in terms of balancing the ISP's utility and the profit made by the ISP. So that was the first topic. In the second topic, we didn't look at the revenue. I mean, we have to at some point look at that. Just look at the ISP's benefit, which is the social welfare or social cost, whatever. And we saw, irrespective of the pricing policy, as long as they satisfy some reasonable assumption, the port capacity purchase game, which is really truly the game that is played, because you're purchasing port capacity and separately you're deciding how to send traffic. Does have equilibria. It can have multiple equilibria. Worst case, the performance might be 8 times worse, but in practice is within a factor of 1.1 or 2. Okay? So that's what's topic 2. Now topic is quite different. Okay, topic 3 is not about sending flows. It's deciding two ISPs based on the topology they have, the traffic demand they have, should they be peering or not. Okay, intuitively, right, if they have a very long transit path, okay, and strategically they are meeting at certain IXPs which can reduce their delay a lot, then they should be paired, right? Okay. Now, when they can pair, if IXP locations are given, I mentioned that there are 140, 134 IXP locations in the US. So if you're ISP, you are an ISP, I am an ISP. If our common points of presence in those IXPs are not in the middle, right, which will allow us to reduce the delays. If they're far away, I mean, then it's no point, right? So it really depends on where the IXP locations are with respect to our networks. And those information, a lot of it is available with data and peering DB, but it's not just based on that. It turns out it's a function of a lot of other variables. So ISPs are associated with many features. So, and they're available. So what, and I think there were like some 20, 26, 30 features. Okay. And some of these seem to be providing very valuable information on whether ISPs should be peering each other or not. Okay. So what my student did is take all these features and figure out which one, which 4 or 5 are the most important. Okay? And then we play with that. At some point he was using 12 features. At some point we trimmed it down to 4 features and so on. And then so those are the filtered features. And then he also created some new features by combining some features and to improve performance. But bottom line is, so with the right set of features, and these are all publicly available features, we could predict with 7% accuracy whether they will be peering or not. Okay, and that's pretty good. And here we are using some machine learning tools. We are taking data. 60-70% of the data we are using for training, and the rest 20-30% we are using for testing. Okay, and XGBoost in this case gave us the best performance. I mean, this is all empirical work. There's not much theory in here, but the observations are interesting. Then we also did it making sure that the any IXPs which are part of the training data set are not in the testing data set. Okay. So in the first part of what you described earlier, IXP pairs, whatever is the training data set is not in the testing data set, obviously. But next we made sure the IXPs, if one ISP has one connection with another ISP in the testing data set, none of the other connections of that ISP are being trained. It models a scenario where you have developed this machine learning model using past IXPs and a new past ISPs, and a new ISP comes in, okay, and lays out a network of routers and so on, and connect to some internet exchange points. Can you reliably predict and tell the ISP that I think based on the network you have laid out, you should be peering with these other already established ISPs? That would be useful service for them. Okay, so so that also we got pretty good accuracy. Yeah. So last but not the least, so peering location. So what I just described in topic 3 is deciding whether they should be peering or not. And that's totally, empirically, machine learning based. Okay? Based on certain features. Features you choose are very important. If you have to throw in too many features, it sacrifices, accuracy. As you know, those of you who are working in machine learning, you have to choose the features right. The first, a lot of the effort actually went in not in running machine learning algorithms, just running the existing algorithm, but figuring out which feature they should use. The last is where you should peer. If you're telling them you should peer, Now, they might have 5 IXP locations in common. They could be peering at 1, 2, 3, 4, or all 5, right? And if they choose, if you tell them, peer at 2 locations, there are 5, choose 2 locations, right? So which of these you should pick? So then we came up with some metrics, which is a kind of heuristic metric, but it works well. There are probably some scope for do some theory as well, but we have not gotten to that yet. By the time my student graduated, is one metric you can obviously see, right? So what you're trying to achieve by peering, you're trying to reduce your latency, right? And I would be interested in reducing my latency, which is the paths going to the internet exchange point. After that, the traffic exists my network. I don't care, right? But the longer the path is, right, the worse it is for me. So if these paths are much shorter compared to the transit paths, and you can estimate those delays as well, then I would be very willing to peer at that location. Okay? Now, but the other agent, the other ISP might have to also feel the same, that it's going to benefit, its path length will reduce by peering at that location, right? So if there's a synergy, then we peer. Otherwise, you don't. A plain game theory version of that actually doesn't have an equilibrium. So that's why we stopped analyzing that. But with some additional assumptions and so on, it's possible to analyze. So, but anyway, so we came up with this metric called, called peering willingness, which captured how much an ISP individually I gained in terms of reducing its path length, and similar for ISP J. And then we combined it in this geometric fashion. Okay? And if one is much worse, if one is very close to 1, that means it really wants to peer. The other is really low, then that won't work. Ideally, both should be 1, so the combined metric is 1, which generally won't happen. When 1 is 1, another is 0.9, it's possible. But 1 is 1, and it's 0.1, this metric is going to be very low. Right? So, and then another metric called peering stability, which says if I have 3 IXP locations which I'm peering, if I drop 1 or add a different one, if I improve the my routing lengths, route lengths by a lot, then I would change, right? So then those choices are not stable. Because that's kind of captures the illusion. And we showed that they have reasonably good prediction on the location. Again, the peering locations are known, and we use some of these to train and some of these to predict. So that's pretty much summarizes the 3 topics we covered. So so let me directly go to the conclusions. So essential insights. Okay, so what we get from this is that constant pricing works well if you really knew the inverse demand curve, which is very hard to know. I mean, our model, we will never know how good our inverse demand, how our lambda curve, although it's based on reasonable assumptions. Proportional pricing, on the other hand, it works great, both in terms of the theory, doesn't require all these lambda curves, and also in practice. Okay? So IXPs could be motivated to use those proportional pricing. Now, if you consider the generalized, which is the true version of the game, then irrespective of the pricing policy, just look at social cost or social welfare. It's actually pretty good. It's within a factor of 2. And the trade-off between this game and the revenue version still needs to be done. This game is already, social welfare game is already quite horrible. The trade-off problem is probably much harder. And the ISP peering decisions, this is all machine learning based. We realize if we choose the features right, and these are all features available across with ISPs, in CADA and peering DB, you could predict pretty well whether they should be peering and where they should be peering. So these lead to some IXP policy recommendations, which we've been talking to IXPs and also some ISPs. Now, where is this space headed? It's not. This is a slowly moving, changing topic. Anything in inter-domain routing, trading, contracting is a very slowly moving. Okay. And right now, peering, they say you peer over a peer. Okay, so basically, people from different ISPs, meet each other, they're salespeople, and talk to each other, say, oh, whether should we be peering or you should be paying me or I should be paying you, whatever, right? So. And they agree, they negotiate that whether they should be peering or one should be a customer, the provider. Everybody wants to be a provider, right? Because they need money. But they maybe sometimes they agree they would peer. And then where they should be peering. So these are decisions that are made, in the yearly, in a monthly, if not yearly time scales. Okay. But increasingly, I think people are realizing that that is inflexible. They want to do automated peering. This small group of people, including some people with startups and all that, started to look at automated peering. I see in the wireless markets also, I think there is some movement towards making wireless contracts automated. So this is kind of using the same motivation, but for internet. But for internet, it moves things even more slowly. But in the next decade or two, I would expect things will change slowly again, because it involves multiple parties, multiple businesses coming together and agreeing. Okay? But hopefully this will provide some direction. Okay? So that concludes my talk. Thank you for listening, and apologies for exceeding by a few minutes.
Thank you, Professor. Are there any questions? If there are no questions, we can close this session. Let's thank the speaker again. And we have refreshments outside. Please continue the conversation there. Thank you.
And I'm around for the early part of tomorrow in the CNI. So if you want to discuss anything, including some of the other topics that I mentioned here, that I've been working on, which I didn't get a chance to present, feel free to reach out to me. Thank you.